Hello and welcome to the 5th week of the Operations Research 1 course. In the 4th week, I've talked about simplex algorithm, and then we've solved several problems, and all problems are maximization and all have a single optimal solution. But that is not always the case. So this week we are going to talk about a minimization case and how to solve it using simplex algorithm, as well as some special cases. And finally, we're going to talk about a method which is called Big M method. So let's start by looking at how we can use simplex algorithm to solve minimization problem. So let's start. Given a minimization problem, so you can see it says that minimize z, so you know that this problem is a minimization problem. We have two methods to solve this problem using simplex algorithm. So the first method is that we convert this problem into maximization. So what we can do is that we multiply the entire row 0 with -1. So remember that if you want to do the first method, you have to multiply the entire row 0. It means that on the left hand side, originally it was z, now it becomes -z. And then the right hand side, you multiply everything by -1. And then now you solve everything using the method that has been described before for the maximization problem. But then don't forget, at the very end of your solution, if you want to have the original value for z, you need to multiply what you obtain here. So when you solve this problem, you will obtain the objective function value as -z. So if you want to return the value into the original z, do not forget to multiply it with -1 at the very end after you finish all the computation. So using method 1, what you need to do is simply multiply everything by -1 and then solve it as maximization. But then at the very end, when you want to return the z value to the original one, multiply the -z that you obtain here with -1. So that's all for the first method. For the second method, which this textbook uses more often, you do the simplex method as usual, except that in step 3, when you ask the question, is the BFS optimal or not, what you check is that whether all coefficients in the row 0 is already less than or equals to 0. Okay, so if you see all the coefficients are already 0 or negative, it means that you are already at an optimal solution. If you still see a variable that is, if you still see at least one variable that is still positive, it means that your BFS is not optimal yet. And then you go to step 4 by choosing that variable with the most positive coefficient as the entering variable. And then for the leaving variable, as usual, you do the ratio test, and the winner is still the smallest ratio test. I write this with a bigger font because this is really important, because no matter whether it is a maximization case or it is a minimization case, the ratio test, the winner is you always pick the smallest. This is very important. So you have to keep this in mind. For ratio test, whatever the problem is, you always pick the smallest. Okay, so let's solve the given example using simplex algorithm. Let's go through step by step. So the first step, convert that given problem, given LP model into standard form. So we add slack variables because originally both have the sign of less than or equal to. So plus S1 for the first constraint, plus S2 for the second constraint. And then do not forget to write down that all slack variables, they also must be greater than or equals to 0. And then the second step is we try to obtain the BFS from the standard form. So if we write down the standard form in the form of the table, you can see that we already have the BFS. So the BFS here has S1, S2 as the basic variables because they have the canonical form here. And then X1 and X2, they are non-basic variable. So we have a BFS from the standard form. So in step 3, we're asking the question, is this BFS optimal? Now we see in row 0, we see that X2 still has a positive coefficient. So definitely this BFS is not optimal. And then because X2 is the only variable with positive coefficient, so X2 becomes the entering variable. And then we perform ratio test, right hand side divided by the coefficient of this entering variable column. So 4 divided by 1 is 4, 6 divided by -1 is none. Remember that the result for ratio test is none if you divide the right hand side with 0 or with something negative. Okay, so the smallest ratio test here is here in the second row, the first row I mean. So the smallest ratio test in the first row, so the leaving variable is S1. Now you perform error or elementary row operation and then using that intersection as the pivot, which means that you are trying to make the column X2 to look like this in a canonical form, 0, 1, 0, where it only has the value 1 where the pivot was, and the other places it should become 0 and 0. So you perform elementary row operation and then you obtain this new BFS, and then you ask the question again, is this BFS optimal or not? Well, while you're looking at all the coefficients here, you don't see any positive number, right? You ignore Z, so you're not looking at this value here. So just looking at the coefficients for all variables, and then you see that they are all either 0 or negative. It means that you have reached the optimal solution for a minimization problem. Now let me ask you a question about the interpretation of the optimal solution that we've obtained in the previous slide. So this is our optimal solution for the minimization case. And then you see here that in this solution, x2 equals 4, x1 equals 0 because it is a non-basic variable, s1 also equals 0 because it is a non-basic variable, and s2 equals 10. Now I have a statement that says the objective function value of the optimal solution is -1 times -12 here. So the z value for the optimal solution is 12. Is this true or false? I will give you the answer after the pause on the video to give you some time to really think about the answer. The answer is false because in method 2 we do not convert z to -z. You can see here that the title of this column is still z. So what we obtain here is already z value. You do not need to multiply it with -1. It's a different case if you're using method 1. Also, the other thing that you may try to convince yourself is that you just plug in x1 equals 0 and x2 equals 4 because that's the optimal solution, and then you will obtain z equals -12. Okay, the second question. Given the problem and the optimal solution where x1 equals 0, the statement says that the first constraint, so here's the first constraint, is a binding constraint. Is this true or false? The answer is true because if we're looking at the table, x1 equals 0 because it is a non-basic variable, and s1 also equals 0 because it is a non-basic variable as well. It means that if the slack for the first constraint is 0, it means that what we consume on the left-hand side exactly equals to what we have available on the right-hand side. Means that we do not have any unused resources for resource 1. In other words, the first constraint is a binding constraint. If you're confused about what I'm talking about, like what is binding, what is non-binding constraint, you need to check out my video on the third week. Okay, now you should be able to perform simplex algorithm on a minimization case, and you are able to interpret the solution of the final simplex table. Now in the next video, I'm going to talk about the special cases that we see in the result of our simplex calculation, in which the optimal solution is not just one. So let's go to the next video.